Game Theory Class 13 Video 2. In this video we're going to talk about Nash's theorem and do another example of the mixed Nash equilibrium. So let's begin with Nash's theorem. So the theorem is quite short and simple, but it's quite powerful and useful a lot of the time. The theorem simply says that every 2x2 game between two people has at least one Nash equilibrium, either pure or mixed. Okay? And an important thing to note here is the following. Some games can have both. So some games have both a pure and a mixed. Nash equilibrium. That's perfectly fine. Some games can have both, but you're never going to have a game which has neither. So this theorem can be used to help you find out whether a game has a mixed Nash equilibrium. Because as we've seen, it takes a lot of time and effort to calculate the mixed Nash equilibrium. So you can sometimes use this theorem to conclude that there is a mixed Nash equilibrium if the game doesn't have a pure Nash equilibrium. So what I'm saying is, if the game doesn't have a pure Nash equilibrium, then it must have a mixed one. Okay, so this is Nash's theorem. Let's do an example calculating all the Nash equilibriums of this game. Okay, so same sort of strategy as I did in a previous video. The first thing I'm going to do is I'm going to label the probabilities with variables. So P, 1 minus P, Q, and 1 minus Q. They need to add up to 1, so that's why I label them like this. Now I'm going to work out the expected payoffs. So E1 of A. If player 1 plays A, they expect to win 1 Q often and 0 1 minus Q often. So that's 1 times Q plus 0 times 1 minus Q, which is simply Q. The expected payoff for player 1 if they choose to play B. If they play B, they're going to win 1 Q of the time and 2 1 minus Q of the time. So that's 1 times Q plus 2 times 1 minus Q. If I simplify this out, this is Q plus 2 minus 2Q, which is minus Q plus 2. Let's move on to player 2. The expected payoff for player 2 if they play X. If they play X, they win 2 P of the time, 0 1 minus P of the time. So that's 2 times P plus 0 times 1 minus P, which is simply 2P. And finally, E2 of Y. If they play Y, they win 3 P of the time and 3 1 minus P of the time. So that's 3 times P plus 3 times 1 minus P, which is 3P plus 3 minus 3P, which is just 3. Okay, so these are the expected payoffs for both players. And I worked these out because I'm trying to work out the mixed Nash equilibrium. And if you recall, the mixed Nash equilibrium is simply a pair of indifference strategies. So now let's try and work out the first indifference strategy. So let's work out the indifference strategy for player 1. This is exactly when E2 of X is equal to E2 of Y. I just worked out what these things are. That's 2P is equal to 3. So this means that P is equal to 3 over 2. Okay, Well, now you need to be mindful of this number, okay? This is a bad number. It's bigger than 1, which is a problem, okay? This means that it's a not possible probability. You can't have a probability bigger than 1. So there is no indifference strategy for player 1. Okay, and because a mixed Nash equilibrium is a pair of indifference strategies, and I know that player 1 doesn't have an indifference strategy, there's no point of me even attempting to work out an indifference strategy for player 2, because I know that there is no mixed Nash equilibrium. So there is no mixed Nash equilibrium. Okay, because a mixed Nash equilibrium is a pair of indifference strategies, and I know that player 1 simply does not have an indifference strategy, so it's impossible to have a mixed Nash equilibrium. Okay, so there are no mixed Nash equilibrium. The next thing to work out is the pure Nash equilibrium. And from the theorem, from Nash's theorem, I know that there has to be a pure Nash equilibrium. So now let's just work out what it is. I'm going to use the shortcut technique. So I'm going to look at the columns, the first numbers, and circle the maximum. So that's 1. And because it appears twice, I circle it in both instances. I look at the y column, there's a 0 and a 2, 2's the maximum. Now I look at the rows, I look at the second number and I circle the maximum. So there's a 2 and a 3, 3 is the maximum. Look at the B row, there's a 0 and a 3, 3 is the maximum. And whenever two numbers are circled next to each other, that's a pure Nash equilibrium. So in particular, there's one pure Nash equilibrium, and that is BY. Okay, so that's the end of this example. We've calculated all of the Nash equilibrium. This game only has one Nash equilibrium, it's a pure one, and it's BY. Some other games will have more than one Nash equilibrium. Some games will have many pure, some games will have many pure and a mixed. Some games will just have a mixed. Okay, that's the end of this example and the end of this video.